This is a, we've got, for 5 or 6 years, we've had a graph analysis package that has about 30 algorithms in it. There's classes of algorithms like cycle detection, like different kinds of graph traversal, partitioning and clustering, path finding, network flow, reachability and impact analysis, and then recently we've added like centrality measures, which I've heard discussed a few times. So just to give an example, let's see. Yeah, here's an example. So like for instance, we have like kind of a very nice multi-way, something like multi-way ratio cut clustering that you could use in an application. It's similar to ratio cut, but it's a different method. And so, for example, here's a simple graph, and not very many nodes, but this one tells you. So we graphically represented that the clustering algorithm says there are 7 clusters. It's just a simple example. For instance, you could do root cause. If you had like why did something crash or fail? You have a whole dependency network, and you see these yellow nodes are like the events, like maybe logs filled up on those machines for some reason. Maybe that's equipment or something. Or you've got a dependency. You want to say, well, what nodes in the directed graph could be the cause of all 3 of those events? And so network flow, root cause would say, it basically traverses backwards and says, well, there's really 14 nodes you really want to investigate, so maybe they're the cause. So that's a way to do something fast instead of, another example would be sorted paths. This is like the k-shortest path problem. Tell me that all the paths between a start node and a finish node, and give me them from shortest to long. It's like, show me 3 ways to get from here to there. What are the 3 shortest routes or something? So this one says, they're given these costs on the links. So this one says there are 24 paths in that, directed graph and then this will iterate through them. So they're getting longer. You can see at the bottom they're getting longer as you go. They're increasing in length. Another example would be, minimum cut, since you were talking. This is how to partition the network at the lowest cost between the start and finish node. That's min cut. So it's kind of a nice, maybe for classroom teaching, maybe for departments or something. And then we've been implementing. Sorry, that's not the one. This is like this is disjoint paths where they're edge disjoint, meaning no edge can belong to more than one path. So it shows there are 3 paths where it's an edge disjoint network, and if you say node disjoint, it would go down to, obviously this node is part of 2 paths, so you should get 2 paths now. So now you get 2 paths existing instead of 3. And then we're doing things like this. We just wrote this a few weeks ago. Centrality, and we color code like by degree centrality. So the darker they are, the higher degree. We just did like between this centrality. This is, I guess, the man in the middle problem. So given that network, you can see, that's the person that's involved in the most paths among all paths, I think, in the network. I'm not a graph theorist, but I sort of. So we're adding algorithms to this all the time, and we use some of these in our graph layout work. So we need graph algorithms in our diagram layout work. So I'll just. So we're, there's about 30 algorithms now, and it's growing. Quit out of that. So this is an example of a 1500 node network, and this is an Ajax. So kind of a no plugin like Yahoo Mail style. No plugins, no flex. It's just drawing networks in a browser. So any browser, Chrome, Firefox, IE, Safari, etc. So I'll just run. So that's a circular layout. I'll run it, but I'll run a symmetric first. So that's a 1500 node network. Run it. It's running now on my 2 gigahertz MacBook here. So that's a symmetric layout. It's all written in Java. So it's only 3 or 4 seconds, and so it's a very fast automatic layout system. So I can go back to compute the cluster-based circular layout. So yeah, the same way. So we're used in a lot of network topology. So here you can see we apply a clustering to the graph. We determine, we do something to have high connectivity within a cluster and few links between clusters. And we provide a visual environment to zoom in. So actually you see the clustering, then we do a circular placement in that cluster, then we do another spring embedder, a constrained spring embedder in the dimension, inside the radius of a circle. Inside a circle, so you actually get smaller clusters because you're actually pulling nodes inside and decreasing the circumference. And then we also do a lot of work in what you call incremental layout, where the drawing, you have an initial drawing, you have changes to it, and how do you preserve the mental map of the drawing for the next. So if you added a few elements of, so I'd like to show a few examples. This is an example of data-driven graphics, where if you were to zoom in, we can have level of detail oriented. You'll see the detail starts to appear as you zoom in and out. So we actually have like what you call a scene, a graphical scene, which is a drawing tree per node in this drawing. So you could, so the idea is people decorate the nodes to show alarms or events, or So the idea is you can do rich graphical front ends. That's an example. Like so you see like the idea of zoom in, navigate on an overview on the right. You see, so you're actually quickly navigating. This is all in JavaScript. So it's pretty fast. So we also do things like the idea of like we could do like projects with drill. You say, well, this is a project called some big task, and then you can drill down into it and show. So you can actually build hierarchy of data. So here's an example. Like I could say here, and this is a storage example. Like that's a storage network where I have some subnet or something with some nodes in it. I can at any time, for instance, edit and say collapse all, and I can call incremental layout. You see how it cleans up the drawing but keeps the relative ordering of everything intact. And then we have things like undo and redo in the browser. So it's actually doing server-side command process back and forth. So it's actually got undo redo stack on the server, and the browser sends requests to the server. So this is these are some. I think this is a nice. This is how the water flows to make the Mississippi River. But that's the tree drawing of all the lakes and rivers, how they flow to make the. And if I lay it out with what we call orthogonal style, this is an example where we have. If I zoom in on this. You see the concept of the drawing opening to adhere to make room for all the labels. So we have this concept of integrated labeling. So it becomes, instead of becoming like just a graph problem, it becomes it turns into a geometric problem of how do you make room for everything that's in the drawing. So anyway, that's an example where if I you see how there's pretty low ambiguity in the drawings to respect. So you can do here you see labels on the nodes, labels on the links. Here this one got longer for the longer name and the like. So that's an example of pure web-based graphical drawings. And yeah, this is I kind of like this one. This is here's one with a lot of connected components, and so we have something called it's called polyomino packing. We actually do we actually compute small, what they call it's like a small rectangular space around components, and then we do type. We don't actually draw a rectangle around every component. So you see how the space they're pulled in tighter here, and all around. So that's you can actually do more packed drawings with this kind of. So it's a way, and then we actually try to keep the relative positioning. So this is actually an email interaction. Who emailed who? And that's a schematic, an orthogonal drawing of the same thing, and we allow nodes to grow. So it's almost like place and route, but you see it's pretty high speed, and the nodes grow to, and so we have a specification where we allow everything to grow. We don't try to fit into a box. We set the spacings between things. Like, so if you have many links that need to route in like a channel between two layers, the layers will separate to allow all the links to flow, and you respect the minimum spacing between everything. So you have all these spacings between links that are running parallel, spacings between nodes and links, and you wind up with pretty good results with that method. I'd like to show here's a whoops. That's strange. Oh, there. So you can kind of see here, like randomize that and compute a symmetric layout with animated drawing. Then we have things like imagine you doubled. So I'm just selecting those elements. If I duplicated those elements, we have the idea of geometric incremental layout. So I don't know if you can see, but I just duplicated there, just to show some effect. So there's twice as many nodes there. So you can see how stable the drawing is so it actually, so actually it's doing geometric, stable, updated drawings as change occurs in the drawings. So for instance over here, if I just did the same here, so you see that, and so actually we do a lot of, so we have what happens when like nodes and links are coming from a network, and you maybe know the cluster to draw them in based on subnet or something else. So that's a circular drawing. That's the same thing drawn. That's what we call symmetric layout. This is a nice method. It's sub-quadratic, so it actually, a lot of your earlier work was cubic, and you could run to maybe 500 nodes. Now we've gotten to tens of thousands on a laptop. So